Welcome back to a new video lecture, and here we discuss a problem related with the kinematic method. So here in this question, calculate the plastic moment capacity required for the continuous beam with working loads as shown in the figure. And here you can observe a continuous beam is given and a 40 kilonewton is acting at a distance of 2 meters from the support A, and the plastic moment it is provided as MP here. And for the portion BC, a UDL with magnitude 20 kilonewton per meter is acting over a distance of 6 meters. So that's the given conditions in this question. So if a question in this way, you have to analyze you have to split them into two parts. That is, first of all you consider this AB, then after BC. So if you observe here the first part, that is the AB portion, you can observe that this plastic moment can occur at this fixed end. Okay, if you consider this portion, it will be act as a fixed support actually. So there will be a plastic hinge will be here, and obviously in this portion also will be a plastic hinge. And when you are selecting this point, the minimum value of plastic moment to be considered, that is, if you consider MP and 2MP, the minimum value is going to be MP. So that is the condition. So if you observe this both values, it is going to be theta. Why it is going to be theta? Actually this load is acting at the center, that's why. So if you substitute those values, you can easily calculate the internal work done. That is MP multiplied by theta plus theta. So you will get this way, this value, and then this MP multiplied by theta. Okay, so it is going to be 3MP theta. Actually you have to provide this plastic hinge at the support. Support means the fixed support. You have to substitute the plastic hinge, and also under the load. Okay, also under the load. So that is regarding the internal work done, and external work done, it is going to be 60 multiplied by delta. And if you take this triangle, you can clearly observe that is theta equal to delta by 2 and delta equal to 2 theta. And if you substitute that value for delta, you will get 120 theta. External work done, it is going to be 120 theta. And if you equate those both the values, internal work done and external work done, you will get MP equal to 40 kilonewton meter. So that's the case of AB portion. Similarly, you have to work out for the next one, that is for the BC portion. In this case, if you observe this diagram, actually it is going to be this, and it is going to be fixed. So actually this portion, a UDL is acting over a propped cantilever beam. So if you consider this one, already we derived an equation for this propped cantilever beam. This bending moment is, the worst position is at point C414L from propped end. Okay, the maximum bending moment is going to happen at a distance of this point 414L. So with the reference of this distance, we consider these values or this plastic moment going to happen. So this value you need to study out. Okay, so if you consider the second portion, that is BC portion, if you observe the distance from this support C, it is going to be 0.414L. Already we derived this expression. Okay, so at that point you can consider the plastic hinge. So if you observe it there, the value is going to be 2MP. Since the BC portion, the plastic moment, it is going to be 2MP. That's the reason. And here also it is going to be MP. Why it is MP? The least value we will consider. So with the reference to these values, you can calculate the internal work done. And if you consider this triangle, similar triangle laws, if you apply, you will get this equation this way. Okay, first of all, this theta 1 equal to delta by 0.586L. Okay, this is a general expression actually, this 0.586L and 0.414L. This is the case for a propped cantilever beam if a UDL is acting over it. Okay, and if you substitute those values, this equations, the relation theta 2 equals 1.415 theta 1. So that's the case. And internal work done you can calculate, that is MP multiplied by theta 1 plus 2MP multiplied by theta 1 plus theta 2. And if you substitute for this theta 2, you will get 5.83 MP theta 1. So that's the case. Then coming to the next one, that is external work done. The total load, that is 30 in this case. Then you have to take the average distance moved in this case. UDL is acting. So you have to take the total distance, it is going to be 6. Okay, the total span length, it is going to be 6 meters. So the average distance, it is going to be 6 multiplied by delta by 2. And instead of this delta, you can substitute the value of this 0.586 L means 6. The total span length, it is 6. So if you substitute, you will get this value, and after that you can equate those equations, this internal work done and external work done, and if you equate, you will get this MP value as 54.28 kilonewton meter. So when you compare this both the values, this MP here you obtained the value as 54.28 kilonewton meter, and here you obtained the value as 40 kilonewton meter. So in this case, you have to take the maximum value, the plastic. When you consider the plastic moment value, you have to take the maximum value. But in the case of collapse load, you have to take the least value. Okay, that's a difference only. So while taking this plastic moment, you have to take the maximum value, and just to substitute those values. In this case, this MP value, it is going to be 54.28. And in the portion AB, the magnitude, it is only MP, so you can directly substitute this 54.28. But in the case of BC, it is provided as 2 MP, so you can directly multiply, and the value, it is going to be 108.56 kilonewton meter. So this is the only case you have to, this case very important, that is, while taking those values, if you compare two values, the plastic moment, the higher plastic moment you have to consider. Okay. So that's the case regarding this consideration of this plastic moment. So I hope the section is clear, and with this we wind up today's section. Thank you.